Hi guys. Okay, we are still in chapter 7, looking at simultaneous equations. We are on lesson 5, and today we're going to look at two other types of simultaneous equations. In other words, their relationships are a bit different than what we've been studying. So far, we've been studying two simultaneous equations that has one solution. In other words, they have coordinates where they both meet. So they have one solution. That's their relationship. Today, we're going to add our knowledge of the relationships of linear equations with two variables. And we're going to look at those relationships that are inconsistent and those that are equivalent. And basically what we're going to learn is that there's three things that can happen when we have a pair of linear equations with two variables. When we have equations that have exactly one solution, which is what we've been working on so far, that's where they have graphs that they intersect at a single point, like this one here. Equations that have no solutions, in which case their graphs, those lines will never intersect. Those equations are said to be inconsistent, meaning they aren't consistent with each other or they're not going to connect. They're apples and they're oranges. And then we're going to look at equivalent equations. Equivalent equations mean their relationship is that they are both concerned with the same line. So they will have multiple solutions. So just to review real quick, this is simultaneous equations that have one solution. They will have a coordinate, like in this case it's 1 and 4 where they meet. This relationship of two linear equations with two variables is inconsistent. And what we'll see here is that they won't have a solution, no solution at all. Okay? And then the last one we're going to look at, those are the equations that can have many solutions. And in that case, their graph are a single line, so they're said to be equivalent equations. All right, so let's take a look at this. In this example, we have x plus y equals 7 and y equals x plus 2. So when we're trying to figure out their equation, we simply can graph what we see, because we remember that all linear equations, if they're placed into the standard y-intercept form, it will be y equals mx plus b. So the second equation here is already in that form. So the first one we need to tweak just a little bit to get it into that form. So let's go down and put it in the form we need. So y equals, and we need to move x to the other side. So in order to do that, we subtract from both sides. So that's negative x, and we leave our 7 there. Okay, so now we know that this is telling us where it's going to meet on the y-axis. So if you look, I've already graphed it. It's up at 7. And we know that m tells us our slope, which is our rise over run. And this is just a quick review. So in this case, we could express that as negative 1 over 1. So as you see, that we then rise, well in this case it's a negative, so we fall down one, and then we run to the right one, and you see how I've plotted that. For the second equation, we start at the y-axis of 2 because that's where it intercepts. And then our x can be stated as 1 over 1. So then that means we rise up 1 and we run over 1. And so we see that indeed these two they have one solution, meaning they have an x and y coordinate. So the next step would be to find the x and y coordinate. And we know we can do that mathematically by setting up our x's and y's together. And so I've just taken the first equation and brought it down. And I've taken the second equation and moved it over where we can have it all together. And then we know we can solve by adding those two simultaneous equations to eliminate one of the variables and solve for the other variable. And then once we do that and we solve for y, we plug it back in to one of the equations to solve for x. And we find our coordinates. Well, in this case, we can just look at the graph where they met. We don't have to do the math. We can just look at the visual representation. And we will see that x, if we count over, is 2.5. And that y, if we count up where that blue dot will be, is 4.5. And so that is our coordinates. Okay, this equation, we do the same pattern. So the first step is we put it in the standard form, and then we graph what we know, which would be the y-intercept, and it would be the slope. And so I've done that below. I've taken the equations and put them in their correct form. And we see that in our first equation, the red equation, we are at 7 on the y-axis. And our slope is a fall of 1, negative 1, and a run of 1. And so that's been plotted out. And then for our green, we see that we start, or where it meets, is at the y-axis at 4. And then we see that our rise over run is a negative 1 over 1. So we go down one step and over to the right, and we continue that. And there we have our dots, and we can make our line. And what we notice is that it has no coordinate. They're not going to cross. They're parallel lines. So looking at the equation, we then can try to do an addition or subtraction of the simultaneous equation to eliminate one variable to see if we can find its coordinates. And if you look, we have x plus y equals 7. We leave that alone. And then we want to line up that x equals 4 minus y. So we leave 4 by itself, and we have to move the y to the other side of the equation. And to do that, since it's a negative, we add y to both sides. So we get x plus y equals 4. And what we notice, if we subtract those, we end up with 0 equals 3. And we know 0 does not equal 3. So these are inconsistent. consistent. They have no solution. Okay, let's look at our third possibility. We've done where they have one solution, we've done where they have no solutions. So let's look at what a multiple solution might look like. So if we take our two equations and we do step one of putting them in the standard form, I'll do that quickly. Okay, so the first one, we have y equals negative x plus 7, moving x over to that side and putting it in the standard form. And I really hope you have this mesmerized, haha, by now. All right, but let's look at the second equation. We have to do just a couple of simple steps to get it there. So I'm going to go down below a little bit. We have 2x plus 2y equal 14. We need to get that y by itself to put it in the form, so we know we can subtract 2x to both sides. So now we have 2y equals negative, well, I'll go back, equals 14 minus 2x. Y is still not by itself, so we divide 2 and we divide 2. And what we see is y equals 7 minus 1x, or x. And then we need to reverse these to get it in the standard form. So y equals negative x plus 7. Okay, I'm going to go ahead and plot that quickly. So I know my y intercept is going to be at 7, which is right on the top here of my line. And I know that I'm going to have to follow a pattern of negative 1 over 1, so rise over run. So I'm going to fall down 1 and go over to the right. 1. So this is our pattern. Now our next equation that we have in red is y equals negative x plus 7. And as you can see, whoops, let me get rid of that. It is exactly the same as down here. So the plot is exactly the same. So they are the same line. And really what that means is that these equations, their relationship is very close. So there's multiple solutions to those equations. And they are said because, of course, they are what? Equal, so they're called equal or equivalent equations. And that is lesson 5 in a nutshell. So just to review, and you might want to pause it and take a note, this is really what we've learned today. When we have a pair of linear equations in two variables, we know we are analyzing relationships of those equations. And we know there's 3 kind of relationships they can have. The first are equations with one solution, and that's where 2 lines intersect on a graph. So they have a xy coordinate. They share that, and that's where they cross. The second type of relationship are equations with no solutions. That tells us on a graph that they're parallel lines. They are not going to intersect. They're going to be parallel. And we call those inconsistent. In fact, it's a fancy word, so I'm going to highlight it. Inconsistent. And then lastly, there's equations with multiple or an infinite number of solutions. And this we know will create a single linear line. And that has a special name called, and I'm going to get a different highlight color, equivalent equations. I hope that helps clear it up. The Jacobs book has a very good example at the beginning of 7.5, and I encourage you to really go back in the book and look through that example. And I'll see you guys in class. Bye.